Hello everyone, my name is Tatsuya Yatagawa from the University of Tokyo. My presentation title is LinSSS, Linear Decomposition of Heterogeneous Subsurface Scattering for Real-Time Screen Space Rendering, which is joint research with Yasushi Yamaguchi from the University of Tokyo and Shigeo Morishima from Waseda University. First of all, let me start my presentation with some impressive pictures. Here's a picture of sushi, a fruit cake, and colorful candles. These stuffs all include translucent materials, and such characteristic appearances of the objects are very impressive for us. Therefore, the representation of translucent materials in computer graphics has been a long-standing goal of the computer graphics studies. The characteristic appearances of translucent materials are described by a physical phenomenon which is called subsurface scattering, so I'd like to briefly introduce here what is subsurface scattering. The left figure is for simple reflection without subsurface scattering. In this case, the incident light from the light source is immediately reflected on the top surface. In contrast, when the subsurface scattering is involved, the incident light enters the object inside. Then the light is scattered many times within the object medium, and finally goes out to the air. Because of the light interaction within the object medium, the characteristic appearances of the translucent materials are acquired. By considering subsurface scattering, the appearance of the translucent object is significantly changed. In this slide, only the simple surface reflection is considered in the left image, and the subsurface scattering is also considered in the right image. As you can see, the right image with the subsurface scattering looks much more realistic compared to the left image without subsurface scattering. To represent the translucent appearance in real-time applications, the screen space method is one of the common approaches. The screen space method assumes that subsurface scattering is approximated by a simple convolution kernel. In the original screen space subsurface scattering by Jimenez et al., the convolution kernel is represented by a weighted sum of Gaussian functions. The convolution kernel is used for the screen space filtering, and broad maps are accumulated to get the final rendering result. Since a Gaussian function is very efficiently convolved by separating it into 1D convolution passes, the overall rendering process in the screen space subsurface scattering is very efficient as well. However, despite of the computational efficiency, these screen space methods are only for homogeneous translucent materials, including human skin. So, the motivation of our study is to establish the screen space rendering method for heterogeneous subsurface scattering. In our approach, the heterogeneous scattering is approximated, but the approximation form we propose can preserve the anisotropy of the scattering. Also, the rendering algorithm using our approximation form is designed to be as efficient as the state-of-the-art method for homogeneous materials. Before introducing our idea, let me briefly review the related work. Due to the limitation of time, we only focus on a couple of studies. The first one is the approximation of subsurface scattering using a weighted sum of Gaussian functions, which is originally proposed for the representation of human skin. Before explaining the detail of the approximation, let me start with the traditional approximation called the Dipole model. Originally, the BSSRDF for general subsurface scattering is a function of 4 parameters, namely incident position, incident direction, outgoing position, and outgoing direction. In the dipole model, the BSSRDF is decomposed into a product of 3 low-dimensional functions. In this form, 2 is the function for the Fresnel effects, which are only dependent on either of incident and outgoing positions. The remaining part is called diffuse reflectance profile, which is only the part that contributes to the translucency of the object involving with 2 positions xi and xo. In the original dipole model, this R sub d is approximated by considering 2 virtual lights, one is above the surface and the other is beneath the surface. On the other hand, the study by Dion et al., the diffuse reflectance profile R sub d is approximated by a weighted sum of Gaussian functions. As shown in the figure here, incident illumination phi is convolved by the Gaussian functions with different sigmas, and the broad map are finally summed up together to get the final rendering result. However, the Gaussian functions used here are simple isotropic functions and cannot represent the anisotropy of scattering only by using them. Also, there are several other variants of the dipole model. They are basically for homogeneous translucent materials and cannot be directly used for heterogeneous materials. Next, I'd like to review the approximation models for heterogeneous translucent materials. Among them, I'd like to introduce a research by Sonneto that is most related to our study. The study by Sonneto introduced an approximation model which is called Subsurface. This approximation model is designed for the material editing on heterogeneous translucent materials. The important idea of their study is the decomposition of the diffuse reflectance profile using two local scattering profiles. This local scattering profile is a radially symmetric function of distance between incident and outgoing positions. Since the local scattering profile is individually assigned to each surface position, it can be manipulated individually as well during the material editing. This model seems to be used in the screen space filtering, but different from the separable Gaussian functions, the square root in the formula prohibits the separation of the diffuse reflectance profile into computationally cheaper 1D convolution passes. Therefore, it is still a challenging problem to achieve as high performance as the state-of-the-art methods for homogeneous materials, even by using the sub-edit representation. Although there are still a number of approximations for heterogeneous subsurface scattering, none of them are well suited for the real-time rendering based on screen space filtering. So from here, I'd like to introduce how the problems of the previous studies can be solved in our research. Our model named LinSSS is based on the approximation model proposed by Sonneto that I talked in the previous slide. In the representation, each local scattering profile is an isotropic function. When R sub d is approximated using the local scattering profiles, two profiles are multiplied and the square root of the product is calculated. Because the local scattering profiles are different in different positions, the local scattering profiles, for example for green point and blue point in the right figure, are different to each other. Therefore, the diffuse reflectance profile R sub d is still anisotropic even after the approximation by the sub-edit. This is why sub-edit is able to represent the heterogeneous subsurface scattering. Furthermore, since each local scattering profile is radially symmetric, it is also possible to approximate the profile using a weighted sum of Gaussian functions. However, the square root included in sub-edit prohibits the efficient filtering even though the local scattering profiles can be approximated by the weighted sum of Gaussians. So the important question here is whether we can remove the square root from this representation. The answer is actually yes. We came across the idea to use a famous inequality between geometric and arithmetic means. As many of you know, this inequality says the arithmetic mean of two numbers is larger than the geometric mean of them. What is more important here is that it also says if two numbers a and b are the same, the arithmetic and geometric means of the two numbers are also the same. Therefore, once two local scattering profiles at x sub I and x sub O are approximately the same, the square root in sub-edit can be decomposed into a simple arithmetic average of the profiles. And we found that two profiles at two different positions can be approximately the same when the target heterogeneous material satisfies two conditions. Here are the two conditions that enable the replacement of the square root with a simple sum. The first one is that the target material is optically thick. This condition is typically assumed in common when the BSSRDF is approximated. Let us consider the local scattering profiles of the two positions. Under this condition, two local scattering profiles decrease immediately to 0 when the two positions are distant to each other. Therefore, when two positions x sub I and x sub O are distant, values of two local scattering profiles must be near to 0. According to this observation, the local scattering profiles at two distant positions will be 0 for both of them. As the second condition, let us consider that the heterogeneity of the material is spatially smooth. Under this condition, it is assumed that the two local scattering profiles will be similar when the two positions are close to each other. Therefore, when the distance between x sub I and x sub O is short, the values of the local scattering profiles will be approximately the same. Eventually, the values of two local scattering profiles will be the same both when the distance of the two positions is long and when it is short. Now the equality in the inequality between arithmetic and geometric means is approximately satisfied. The square root in the approximation form of the previous study is decomposed into a simple average of two profiles. In other words, the diffuse reflectance profile is linearly decomposed into the average of two local scattering profiles. Furthermore, each local scattering profile is a radially-symmetric function, therefore we approximate each local scattering profile using a sum of Gaussian functions. In our formulation, the weights for the Gaussian functions are different for each position, and the sigmas for the Gaussian functions are the same for every position. Now, the final approximation form of LinSSS is shown in the bottom. As you can see, this form is a linear combination of only Gaussian functions. Considering that numerical convolution of the Gaussian functions can be performed efficiently, it will be useful for the real-time rendering based on the screen space filtering. So let us substitute the LinSSS representation introduced in the previous slide into the subsurface scattering equation, which is a generalization of the rendering equation. By skipping the details, we can get the equation shown here. This equation computes the radiant exitance from the incident radiant flux using the PSSRDF represented by the LinSSS parameters. In other words, the output image, which is equivalent to the radiant exitance m, is computed from the input image, which is equivalent to the incident radiant flux phi. To evaluate the right-hand side of this formula, we need to compute the convolution with the Gaussian functions 2n sub g times, because each term in 2 dimension requires to compute a convolution. Since the convolution of 2D Gaussian function is separated into two 1D convolution passes, the total number of the 1D convolutions needed to be computed is 2n sub g times 2, which is equal to 4n sub g. Compared to the previous approaches for homogeneous subsurface scattering, 4n sub g is a little bit complicated, even though our LinSSS can be used with heterogeneous subsurface scattering. So we try to reduce the computational cost to evaluate this equation. First, we introduce a relaxation to reduce the number of the convolutions included. Please look at the term in the first dimension. Long story short, this term can be approximately transformed by distributing the Gaussian convolution to the functions multiplied in the parentheses. This approximation is given by assuming the incident radiant flux phi is spatially smooth. Please look at the supplementary document for the detail. By substituting this approximation, we can rewrite the equation like this. And by factorizing the common convolution terms, we can transform the formula like this again. In this formula, this blue part can be pre-computed when the LinSSS parameters are loaded. Therefore, the convolution that we need to compute runtime is only those highlighted by a red circle here. The number of 1D convolution passes is the double of the number of the 2D Gaussian convolutions, so the number of the 1D convolution passes now decreases to 2n sub g. However, this is still not as efficient as the state-of-the-art method, namely the separable subsurface scattering. To further speed up the computation, we next focus on how the convolutions are computed. Simply thinking, Gaussian functions we need to convolve with are Gaussian functions with different sigmas, and they are all convolved with the same phi. Suppose that the sigmas are indexed in order of increasing value, blurriness of the filtered images increases following the increasing value of the sigma. Therefore, instead of calculating each convolution individually, we calculate a filtered image by interpolating two other pre-filtered images. In this slide, the input radiant flux is convolved with the Gaussian functions with predefined sigmas, and these sigmas are given by doubling and doubling the predefined lower bound of the sigma, which is denoted by sigma sub 0. When a sigma sub I is in between two neighboring predefined sigmas, the convolved result for sigma sub I is computed by interpolating two images as in this slide. When an image sequence is given by Gaussian filtering with such increasing sigmas, its spatial resolution gets lower when the value of the sigma gets larger. In this case, we can reduce the size of the image when its spatial resolution is small. Then, we can get the image pyramid that can be stored in the MIP-map supported by the graphics API. Since the interpolation of images in between two neighboring MIP levels is supported by the graphics hardware, we can calculate the filtered image with arbitrary Gaussian sigma efficiently by hardware-supported interpolation of the MIP levels. When constructing the MIP-map, only what we need to do is filtering the image sequence in which the image size gets smaller and smaller. Therefore, the overall computational cost for the filtering is given as the sum of the geometric series. Now, the geometric ratio of the series is 1/4 because the size of the image in the higher level is 1/4 of the image in the lower level. Therefore, the overall cost for filtering is at most order n for n pixel image, and the cost for each pixel will be at most order 1. Eventually, the overall computational cost after accelerations introduced here is only order 1, which is as efficient as the state-of-the-art method, the separable subsurface scattering for homogeneous materials. Now, LinSSS achieved the objective of our research, namely the screen space rendering for heterogeneous materials, which is as efficient as the state-of-the-art method. So from here, I'd like to show you some experimental results. Let me show you a demo movie first. In this movie, our method is used with 4 different lighting conditions. As shown in this movie, our method can be used with arbitrary kinds of lights, including point light, directional light, and environmental light, because our method is an extension of screen space method. I think as far as you can see the result in this movie, the rendering result is sufficiently natural. Since the time is limited, please watch the movie in our website for the results for the other materials. Now let us compare our rendering results with previous approaches. Here are the results of previous screen space methods and our method. I will compare each of these methods one by one from the next slide. For reference images, we used ordinary Monte Carlo path tracing with an octree-based hierarchical integration method for the light path traveling through translucent materials. First, our method is compared with the screen space subsurface scattering, in which the BSS-RDF is approximated using a simple weighted sum of Gaussian functions. Looking closely at the results of the screen space subsurface scattering, the detailed texture which we can see in the reference image is blurred out. On the other hand, our method has succeeded in preserving the detailed texture, and we can see the heterogeneous subsurface scattering is preserved in our rendering. Next, I'd like to compare our method with the separable subsurface scattering, which is one of the state-of-the-art method for real-time rendering of subsurface scattering. The result of the separable subsurface scattering is a little bit blurry, and furthermore, we can see the stripe artifact in its result. This stripe artifact is due to the improper separation of the diffuse reflectance profile into 1D convolution passes, because the diffuse reflectance profile can't always be separable into the 1D passes. Again, compared to the separable subsurface scattering, our method has succeeded in representing heterogeneous subsurface scattering. Finally, I'd like to compare our method with and without the acceleration. As you can see, the results for both images with and without the acceleration are close sufficiently to the reference image, but the computational costs for them are totally different. Without the acceleration, the computational time for the screen space rendering using LinSSS is as much as 87.1 milliseconds. On the other hand, with the acceleration, the computational cost can be significantly reduced as much as 4.3 milliseconds. Here is a comparison of the computational time. With the acceleration of the computation, our method has become 20 times faster. Also, the computational time after the acceleration needs as much as the separable subsurface scattering, although our method can be used with heterogeneous subsurface scattering. As we explained previously, the order of the computation time is the same between the separable subsurface scattering and our method. This is also proved experimentally as shown in the chart in this slide. Okay, so let me conclude my presentation. In this presentation, I introduced LinSSS, a linear decomposition of heterogeneous subsurface scattering, which can be used for real-time screen space rendering, and which is computationally as efficient as the state-of-the-art method for homogeneous materials. Also in our paper, we provided how we can get the LinSSS parameters from measured data, more elaborated comparison of rendering results, and the evaluation for the approximation accuracy. If you are interested in these contents, please look at our paper. Now that's all for my presentation. Thank you for listening. Also, on behalf of the authors, I'd like to thank the people listed here. Thank you.